Okay, thank you very much, Shirley. Yes, I'm glad to be here, and I prepare a few words regarding myself, so to the audience get to know a bit of me first. Uh, so I'm going to be talking about sustainable massive IoT, and as Shirley mentioned, I'm assistant professor in sustainable wireless systems here at CWC. So let's move forward. So this is a bit background on me. I got my bachelor studies degree in Cuba, in Central University of Marta Abreu of Las Villas in 2013. And then I was working as a telematic specialist in the Cuban telecommunication company for 2.5 years. After that, I went to Curitiba, Brazil, where I did my master's studies in 1 year. And then I came to Finland for my PhD studies, which I did since 2017 to 2020. After that, I was working as a postdoc for 1 year, and then I got my assistant professorship last year, which is based on sustainable wireless systems, as Hirle mentioned before. So this is basically me, but if you want to know more, well, you can contact me always or check my profiles in the web. I'm going to be talking about massive IoT and how sustainability is involved there. So basically, as maybe you already know, or have you been taught during this MTC course, the number of IoT devices is exponentially growing and growing. Basically, it's driven by the need of turning out our homes, the cities, buildings, our works, the environment, health, industry, anything into smart, into autonomous and sustainable, interactive and intelligent systems. We can find IoT in every aspect of our modern life, like for monitoring agriculture applications, environment, health, like for enabling smart environments such as home, buildings, and social services, personal gadgets, smart clothes, watches, everything is there. So the number of IoT devices is in the order of billions nowadays. Billions of IoT devices are coexisting, and this creates several challenges that we are going to mention later on. This is a nice illustrative figure on how the market is split regarding, this is for 2 years, 2019 and 2030, the prediction for in a decade. And you know that you can see that the number of IoT devices is going to triple or more in these years, in a decade, which is huge. And it's in the order of billions and trillions, the revenue. And maybe most of these devices are in the area of media devices, but also in low power communication devices like in smart grid, connected vehicle, lighting, asset tracking, and inventory management. And the market is quite split between North America, China, Europe, and the rest of the world. So these are the three main markets: North America, China, and Europe, because the rest is split into the rest of the world. But yes, this figure says basically that we are experiencing an exponential increase, and the worth of this market is huge. Regarding 5G and IoT, we must say that 5G is the first cellular technology to natively support machine type communications, which are the backbone of the cellular-based IoT connectivity. So as you know, cellular-based IoT connectivity is nowadays focused on two main regimes, like critical IoT or URLC, and massive machine-type communications. There is, of course, the non-cellular sector business, which is taking a big slice also of the market nowadays, but for the sake of simplicity, let's focus on the cellular-based IoT in this first slide at least. So yes, the 5G IoT have two main regimes, massive machine-type communications and URLC. However, this distinction will blur over the coming years because of the emerging use cases and the and the verticalization of service provision. So this will demand stricter and higher level service guarantees, including multi-dimensional optimization and scalable designs. So what is the vision of IoT in the 6G era by 2030? For understanding this, we may need to revise what we understand as sustainability, because the sustainability might be the core component or aim of 6G and IoT in the next years. So sustainability, what is sustainable? What is sustainable IoT? I'm not sure if any of you want to raise hand and give his vision or want to write it in the chat. I don't know. What do you understand by sustainability? Let's see. So many people, or most of the people that are not directly working on this, usually match environmental friendly or green networks to sustainability. But sustainability is a much broader concept. Sustainability is commonly defined as the ability to meet the needs of the present without compromising the ability of future generations to meet their needs. So basically, basically we cannot compromise the future or the ability of future generations to meet their needs. So that's basically one of the definitions of sustainability. Beyond some sufficient level of continuous functioning, however, sustainability represents more than just the mere ability to survive, but to drive. We need to progress. So maybe a more appealing concept of sustainability is this one here below, which is that it's an assembly of mutual interests between social equity, viable economics, and a healthy environment. And for that, we have this triangle here, which represents or personifies a synergistic integration of the three main competing interests, including equity, environment, and economy, or what it is known also as the 3 E's. So basically, any sustainable solution is quantified or somewhat can be qualified in terms of these 3 parameters, and that defines then the sustainability of the solution. The thing is that it's difficult to quantify it, that's for sure, because these are usually conflicting how do I say, conflicting dimensions of the sustainability problem, because we can grow the economy, but in many solutions by growing the economy, we are affecting environment or equity. So it's a conflicting triangle that we need to find some equilibrium there. So here in this figure, we also showed or illustrated the relationship of 6G with the Sustainable Development Goals of the United Nations, which are these 17 illustrated here. So no poverty, zero hunger, etc. There are 17 of them, and maybe in the second slide we can go over a few of them. So here we can observe that 6G will cover a wide range of setups from global global regional deployments as in traditional cellular systems, allowing roaming and economies of scale of equipment, while wide area coverage continues using mainly low carrier frequencies. So 6G will bring specialization through local network deployments and introduce also hyper-local specialization with very high level of granularity, especially exploiting higher carrier frequencies like millimeter wave and terahertz. All these will be essential building blocks to support these sustainability development goals of the United Nations. So 6G target a much more ambitious approach than 5G. Basically, the aim is at enabling intelligence, data, sensing, actuating, processing, and connectivity everywhere. So obviously for enabling this, we need to have massive IoT deployments because they are at the core connectivity of the system, of the society. So 6G, many researchers say that 6G will connect the unconnected. So we will connect everything. Well, this we will see if this is possible in 6G or later on. But yes, if we enable the connectivity of everything, then we are going to strengthen the economy in a way that works for people and enhance people well-being. And that basically enables sustainability. That's the goal. So these are a few examples on how 6G IoT and United Nations Sustainability Development Goals are matched. For instance, we have zero hunger. And the basic example is that ICT technologies, for instance, can help farmers improve crop yields and business productivity through better access to market information, weather forecasts, soil monitoring, and obviously also ICT-enabled watering of fields. We have also this other SDG, which is related to good health and well-being. Obviously, the mobile communications enable communication with medical practitioners, monitor well-being through mobile and other wearable sensors, provide access to health programs, and big data of epidemics. So it allows access to digital medical records, remote patient monitoring, etc. We have also IoT in smart water management, enabling intelligence there and monitoring water supplies as well as necessary interventions, enabling practitioners at the local level to ensure the equitable and sustainable extension of water, sanitation, hygiene, etc. The 7th UN SDG is related to affordable and clean energy. So obviously mobile communication can help via providing data analytics to determine viability of renewable energies. Also to provide online resource for clean energy procurement. Also smart grid solutions, distributed energy systems, smart metering, and many other ways. In terms of industry innovation and infrastructure, which is this term 9 here, mobile networks are critical infrastructure to provide affordable access, not to voice and data, but many services that are emerging nowadays, and to provide also sustainable manufacturing. In terms of sustainable cities and communities, well, advanced communication techniques can, of course, attract and retain workers in rural areas by improving the teleworking experience, allowing for collaborative innovation systems among firms and research centers, and increasing efficiency of rural businesses and training of workers. Drones can also be used to boost productivity of rural areas and businesses, improve access to goods, etc. And yes, 12 is related to responsible consumption and production. I'm not going through this, but well, why not? Dematerialization, virtualization is related here, cloud computing, smart grids, smart metering. But we need to take into account also here that there is inconvenience because it generates e-waste. Technology generates e-waste, which is a problem in terms of environment friendly solutions. And to conclude examples, we have climate action. So obviously mobile communication can help avoid greenhouse emissions by enabling other sectors to reduce their own emissions, facilitate smart traffic management, smart urban lighting, smart parking, smart logistics, building energy management system, remote working, sharing economy, etc., etc., etc. So yes, I was mentioned before that it's important to keep in mind that the advancement of one of these goals might impose adverse effects on others. So when considering 6G and mobile communications technologies and IoT and their development, it is important to keep in mind that the developed technology itself should be sustainable and used in a sustainable way. So those are the main principles that guide or that drive research and industry in the path towards 6G. So our aim, basically more focus on technology aspects, are related in terms of IoT to solve these challenges, to solve the challenge of long lifetime. So we need to have devices that last for long. So we avoid the problem of e-waste from from handling the battery recharging and the battery problem in general. To have solutions with low maintenance to so in this way we can benefit the economy of the solution. So if we reduce the maintenance, we are promoting more economical solutions. So we are not wasting that. Minimum e-waste to avoid environmental affectations, and we need to provide still reliable connectivity. Reliable here means that we need to provide the applications with the required quality of service guarantees. So basically, our aim when looking for IoT solutions with these challenges is to investigate and propose energy efficient solutions, algorithms, and protocols, as well as low power distributed architectures and novel green technologies to enable sustainable IoT by addressing these specific challenges. So in this lecture, I'm going to be referring to one of the main problems related to the IoT and the massive IoT, and it is the charging problem. So as I mentioned before, the number of IoT devices is nothing but growing, especially in comparison with traditional ICT equipment like laptops and mobile telephones, which you can see here in this graph that they are expected to stay and growing or growing very little over the past of the years, while IoT solutions will be increasingly growing, right? So in any way, a general problem here for all these ICT solutions relied on the wired aspect. So wired charging is cost prohibitive to deploy at all the locations necessary to make them useful. And the same is true for battery power solutions. This is what I was referring before. This how do I say, this magenta blue like bars here are referring to the number of IoT devices that is increasing, and this one is not increasing, but they have other problems. In the case of the first case, in the high increased number of IoT devices, the problem is with the charging, because you cannot deploy cables to charge the devices everywhere. You are creating a problem, a web problem of cables. And also the battery is a problem because if you start using battery for all these devices, then you are replacing the problem of the wires for another problem, maintenance and e-waste. You are increasing the number of maintenance that you need to run over these devices, and you're increasing the e-waste problem. In case of this second group of devices, the increasing number is not significant, but they can work well with wire charging and batteries without causing extra penalties with respect to current scenarios. But people more than ever are seeking for an uninterrupted and flexible online connectivity. So they want to maximize the time they remain with the active phone or tablet. So they don't want to spend time waiting for the device to be charged. So would it be nice to have wireless charging in all these cases? Well, the answer is yes. But is it possible? The answer is more uncertain in that case. So for these two kind of problems, we are seeking for wireless charging solutions, because if you have wireless charging, then you remove the cable problem, the battery problem, and the always on, and you enable always on activity that was not completely available before. So for the first group, where you have massive IoT number of devices, the main question is how to enable and realize scalable low power wireless charging. While for the second group, which are more energy hungry devices, the question is how to realize safe high power wireless charging. And we're going to go a bit over these two questions over the remaining slides. So here are some interesting examples on the use of energy harvesting technology for charging IoT devices and other devices as well. For instance, here we have this low power RFID tag that harvests energy from ambient light and also from RF energy, so from the signals that are in the environment already, those signals that are using our phones or any device. Here we have, for instance, this other device, which is an energy harvesting link wireless sensor that harvests energy from piezoelectric, electrodynamic, and thermoelectric generators. This AmbiMax wireless sensor node with a solar panel here and a wind generator. This is an interesting example where we have a functional prototype of piezoelectric power RFIDs mounted in these shoes. So they are charged while the person is walking. This is in a bigger scale where we have a cellular base station powered by a hybrid of solar and wind energy. So this is the so-called zero energy base station. So the net energy consumption of this base station is zero because it's consuming energy, environmental energy. And we have this Titan Aerospace solar power UAV for delivering wireless internet access to developing nations. So all these solutions somewhat promote sustainability as they reuse readily available energy in the environment. However, that basically is the main inconvenience here as well, because that energy is random, may not always be available, and it's mainly location dependent. I mean, the location really influences that if you can leverage this energy or not. So there are some few other cases where a specific source of energy and planning this energy is needed, and that is the case of well. But before that, let me discuss this. This energy harvesting setup, like when you have these energy harvesting nodes harvesting energy from the sun, and then you have these information access points. So basically, these devices rely on the energy, on the solar energy, to operate and send information to the access point. And as I was telling before, the external source of energy can be anything, depends on the specific application. Obviously, in a place as Finland, we cannot rely too much on the sun, especially in winter. In winter, but there are many other sources of energy. And then the main thing is this energy comes free. You don't need to pay for it. But as I was telling, it's intermittent and controllable. And maybe the most important thing is that the transductor to convert this energy to energy that can be used by the device is usually bulky and costly. So these create important limitations in terms of IoT devices because they are usually very small devices. And as this is, for instance, an illustration on 4 main ambient energy sources. The first 2 are related to light energy from indoor and outdoor, the solar. And you can see that they provide much more energy provision in terms of energy per area than thermal and radio frequency. But the hardware complexity is higher, and they are sensitive to blocking. While, for instance, if you rely on radio frequency energy harvesting, which is harvesting the energy that are in the environment, the energy provision is very, very small, several order of magnitude lower than this. But the hardware complexity is very low as well. So you gain on this, but you lose on this. Those are the basic trade-off that are available everywhere in the world of engineering. And this is an interesting illustration of how this energy availability influences or limits the actual practicability of a system or a design. Where you have for instance, if you have a RF solution where you are using the Wi-Fi access points in a room, if I recall correctly, yes, this is a room of 24.5 square meter. So you have several access points there. So what kind of electronics can you power with those access points? Well, with 2 Wi-Fi access points, you can power a smoke detector or a mouse. If you require to power a wristwatch or a digital thermometer, you would require 6 access points. And that number starts increasing. And if the idea is to power a smartphone, a single smartphone, then you would need more than 20,000 Wi-Fi access points. So obviously this is not a solution for this. And energy harvesting from ambient sources, like those ones that are available in the environment from radio frequency sources, cannot be understood as a mean to power this kind of electronics, of course. This is for powering very low power devices in the like sensors, and even sensors, it should be very energy limited sensors. So yes, this is basically the idea behind this. If you want higher energy provision, you should go for other energy sources or go to the domain of the wireless power transfer. But before going that, let's see another thing regarding this. This is like a different kind of sources, like Wi-Fi IP. This is a TV tower, and this is an isotopic transmitter. So here we have the transmit power, the frequency of operation, the distance where the harvested energy is measured, and this is the harvested energy. So in all the cases, you can see that the energy is in an order of microwatts or lower. Here we have nanowatts and lower. But see, this is the order of magnitude, 96 kilowatts TV tower, and you're measuring the harvested energy at 4 kilometer. So it's, and the harvested energy is 60 microwatts. Very importantly, the path loss, which is the main factor that limits the harvestability of energy, because it's the one that affects the channel conditions, increases with the power of the distance and with the square of the frequency of operation. That's why even when you decrease the frequency, like going to 1 megahertz, for instance, you can increase the amount of energy that is harvested. However, operating with this frequency is not the way to go in IoT, because this requires high form factor antennas. It's not feasible. We're looking for solutions that operate in the region of sub-gigahertz or several gigahertz. So in this order. And yes, and also, as I was mentioned before, relying on these kind of sources is subject to interference, not interference, but blocking and availability. So it's not it's not usually a solution where you can guarantee quality of service performance metrics. So when we are talking about energy harvesting solutions, what can we do to enable or improve the performance of these kind of networks relying on these ambient sources? So basically, one thing we can do is to study and predict the energy sources availability and plan the energy harvesting deployments of these IoT devices accordingly. For instance, let's say we have 3 points, which are the epicenter of a certain energy source. And as the distance from these points decreases, the energy availability decreases considerably. So basically, if we have these 3 points, obviously the points or the regions, the area regions where the energy availability is the greatest is around these points. And in the middle, there is another area where the energy can be lower, but still significant. Then in the remaining zone, the energy availability is going to be low. And at a certain point, then you cannot harvest any energy because energy availability is considerably reduced. So the critical issues here is how to predict these areas, and also the fact that these areas can vary over time and from region to region, because these energy sources are maybe random or maybe moving. So in any case, you need to do a statistical analysis of the energy availability. And for that, what people usually do is either to run measurement campaigns, which are tedious because they usually take quite a long time and they get updated soon, or they develop some tractable models and analytics that are somewhat based on smaller scale measurement campaigns, and they can be extrapolated to greater setups, and they work with those. It's possible, but it's difficult for sure. So one of the tools that is used for these tractable analytical models, I guess you have heard about it, is related to stochastic geometry, but I'm not going to go into that here in this lecture. One other important thing is already related to the energy harvesting circuit itself. So a traditional single band harvester looks like this, where you have a single antenna tuned to a single band. However, the energy harvestability here is very low as compared to a setup where you can have multiple antennas and can harvest energy from different bands of frequency. So if you have a setup like this, you can obviously increase the energy availability at the end, at the DC output. However, the main issue here is that this multi-band operation often requires of multiple circuits operating individually in distinct bands. So such design increases the complexity and cost of the system in general, and maybe, of course, inappropriate in massive low power, low cost IoT use cases. Here we have an alternative, which is a single circuit prototype with dynamic frequency tuning. So you are simplifying the circuitry. You still can have the gain of the multiple antennas, and you can switch this to select the antenna or the bandwidth with the best performance dynamically. So this is preferable in terms of, this like trades performance for low complexity. So it might be good in case of IoT. Here we must say also that this comes also with several challenges, but we know go over them here. One thing to keep in mind is that equipping more antennas for more energy harvesting capabilities might not be always feasible because of the device's form factor. So if you increase the number of antennas, you're increasing the device form factor. And depending on the use case, that might not be possible. So you are usually have a constraint on the form factor, and then you design based on that. Also, another approach is the use of large-scale harvesting surfaces. So research community and industry in general are considering meta-surfaces, metamaterial-based antennas, and reflect arrays as key in the next generation of wireless systems. So this is basically because of their associated extremely low hardware footprint, which enables cost-effective embedding in various components of the wireless propagation medium, like in building facades and room walls, for instance. So although the focus has been on efficient information transmission in wireless communications, we also envision that these harvesting surfaces can be more leveraged to aid the wireless radio frequency transmission systems. So, for instance, we envision that they can be also used in building facades and rooms, wall ceilings, especially in combination with other harvesting surfaces, like for harvesting sun during day and harvesting radio frequency energy during night, for instance, and other kind of implementations. So basically, we have other examples of integration of energy harvesting into other materials, like this textile integrated rectangle array, where and we have also this antenna array here, which is in a glass. This is a microstrip batch in a glass. So, for instance, this can be exploited for quasi-invisibly installing it in a window or anything without compromising their origin function. Yes. And as I was mentioned before, they can be combined with other energy sources for further improvements. Also, as I was saying before, multiple antennas are maybe needed to provide further energy availability, because you can harvest energy from different antennas and then combine them. And there are basically 3 different kind of architectures to combine the energy. you can have DC combining, where each antenna is connected to its own rectifier, and then the energy is combined in a DC circuit. You can have RF combining, where all the antennas are arranged to channel the RF power through a single rectifier. And hybrid combining, which basically combines these two extreme approaches, as you can see. So DC combining provides broader bandwidth than RF, so allowing energy harvesting from a broader range of incident directions. However, and this is basically because with this architecture, you cannot create receive beams, which basically you can do with this. But anyways, the main challenge here, or the main drawback, is that the rectifiers must individually rectify very low input RF powers here. So the performance of each of these rectifiers is much worse than the performance of this one alone. But on the other side, the main inconvenience of this is that this is creating beams. So it's difficult to configure those beams in an ambient RF energy harvesting scenario where you don't know the direction of the from where the energy is coming. That's what it basically means. And this is basically combining these two approaches and trying to trade one thing by the other and do a moderate design, taking the benefits and the efficiency of both approaches. And for instance, I was about to mention that the state-of-the-art research on prototyping considers the DC combining, or RF, as I was mentioned before, mainly. However, with the development of low power architectures, low power integrated circuit designs, and ultra thin energy harvesters with much more energy efficiency and dynamic implementations may be at hand. Specifically, for instance, in this case, RF combining, this architecture is usually fixed. So you cannot tune the beam, the energy beam, or the beam that you create to capture the energy. But in this case, in one of our papers, we're proposing to be able to dynamically tune this RF combining circuit, so you can tune the beam according to the measurements that you made of the energy that you're harvesting. So basically, you would harvest energy, and based on those measurements, you can tune this circuit here and move the beam to match one of the key directions of the energy. So that's basically the main intuition here. So yes, that was an overview of energy harvesting from ambient sources. But as I was commenting before, one of the other alternatives, and the one that is most promising for guaranteeing quality of service performance, is related to wireless power transfer. Wireless power transfer, what is different from energy harvesting is that there is a dedicated energy transmitter that is dedicated put there to do its job of wireless charging the devices. So there are basically three kinds of technologies: relay inductive coupling, magnetic resonant coupling, and electromagnetic radiation. So basically these two categories, the first two, are the most available categories in the market because they are the ones that provide the best or the more energy possible. The thing is that they are designed for short range charging and have limited multi-user support. Maybe, and very importantly also, they still limit and confine the maneuverability and mobility of the device being charged, which limits their scalability. So it's very important, especially in terms of massive IoT. You can see this example of inductive coupling, this QI wireless mobile device charging standard, this electric booth. If you are wondering, the electric booth brush uses also wireless charging in his inner circuits such that it avoids the risk of electroshock when it's in your mouth. It's an interesting application. Also, there are wireless power medical implants using inductive coupling. And as an example of magnetic resonance coupling, we have this Qualcomm Halo electric vehicle, which is being powered by a charging pad, and this higher wireless power HTTV. This is on as well. But as I want to highlight that these solutions are for energy hungry devices, and there are some constraints on the maneuverability and also on the charging distance and the multi-user support. Meanwhile, this electromagnetic radiation-based wireless energy transfer is mainly for low power devices, and it allows multi-user support and large charging range. We have this also, these are basic in radio frequencies, so energy, but this sharp UAV is receiving energy beam from the ground using a laser. This is another approach, but we will be focusing on these solutions in the following, in those based on radio frequency. So different from ambient radio frequency energy harvesting, radio frequency wireless power transfer systems are characterized by on-purpose energy transmissions from dedicated energy sources, which are also called power beacons. That's why the single PV, the acronym PV comes. And here, for instance, we can see an infrastructure-based architecture and an infrastructure-less architecture, where the energy and information is interchanged peer-to-peer. And here we have like a base station and an energy transmitter. The base station can also be transmitting energy to a device. They have their coverage area. Obviously, in this intersection area here, the energy availability can be significantly higher, as it is the closest to the both nodes. And there are interesting insights into that based on this. What is important is that the power beacon itself, which traditionally is connected to a power grid, can be also connected to green energy sources. And in that case, the ultimate energy that arrives to the devices come from the environment. That is what we say that is a truly green solution when the energy comes from green sources. As you recall correctly, we cannot equip this device, assuming that it's a sensor or something like that, with a transductor to harvest this energy because of the form factor. But we can equip this bigger device with this and then transfer the energy radio frequency to the device. That's the main thing here. So what are the main challenges of radio frequency wireless power transfer? Why is not so popular nowadays still? Basically because of the low end-to-end power efficiency, because as you see, in this region of short distance, the efficiency is quite smaller compared to inductive coupling and magnetic resonance coupling. And when you go farther beyond 1 meter, the efficiency decreases exponentially because of the path loss. So it's difficult to promote the efficiency in a system where the efficiency of the energy transfer is very small. One other key aspect that is usually overlooked is the fear of wireless. So people's concerns over exposure to radio waves are rising with the 5G and the exploitation of the higher frequency bands. This is even when the radio frequency transmission in such bands is non-ionized. So these transmissions cannot change the structure of atoms and molecules, which would lead to carcinogenic effects, for instance. Nevertheless, there are some limits to promote safety because these radiations at very high frequency, like millimeter wave, can still impact somewhat the biologically our bodies, like increasing the temperature. That's an effect that can happen at very high frequency exposure, radiation exposure. That's why there are certain limits imposed by regulatory bodies and organizations worldwide to limit the radiation. But still, we need to come up with transparent mechanisms to remove this fear of wireless that is increasing, and it's not rational, but it's there. So we need to deal with it. And lastly, but not least, we have also a lack of technology standardization. So the solutions that are already available are not completely standardized. They are more ad hoc. So standardization is needed, is required, especially to guarantee technology interoperability. So the end users don't know which wireless charging technology they are using, and of course, open the market then. And the standardization in radio frequency wireless portfolio is incipient, as I was mentioning. But it's important to see that as if you especially handle this issue, low end-to-end power efficiency, so you make the system more profitable and more sustainable, and you handle these other challenges, then of course you're propitiating more attempts of standardization because the technology becomes more attractive. So by handling these two, we are trying to also handle the third one. So the final goal is to design high end-to-end efficient architecture and radio frequency charging protocols transparently complying with electromagnetic field exposure regulations, which is basically related to these two goals. Those are the technological challenges. And as a result, we can target the third one. Regarding radio frequency wireless power transfer, we can go back again to the question that how to enable or realize scalable low power wireless charging, specifically to massive deployments of IoT devices. And we do envision that the wireless power transfer will be an important building block of many popular commercial and industrial systems in the future, including, of course, Internet of Things, Internet of Everything, RFIDs, large-scale wireless sensor networks, etc. And for this scenario, the question is this one. And for that, we have introduced, like 2 years or 3 years ago, the term massive wireless energy transfer, which specifically refers to that, on how to power this amount of this very large number of devices, ultra low power devices. There are some representative players on this kind of technologies. For instance, we have transfer fee and power cost. They sell solutions for this kind of problems, charging a massive or large number of IoT devices, low power IoT devices. And you can check, of course, their available products in their web pages. But the most important is this figure I would like to discuss here. Let me go back. Yes. Which illustrates how the radio frequency wireless power transfer technology can be more sustainable than the traditional wire charging and battery power alternative. And the figure itself illustrates the capex and opex for an industrial IoT scenario with 30,000 sensors in the industry location. I'm not know if you are aware, but the capital expenditures are the funds used by a company to acquire, upgrade, and maintain physical assets such as property, plants, buildings, technology, or equipment. So basically, capex spending is important for companies to maintain existing property and maintain equipment and invest in new technologies. While operational expenditure, OPEX, is an ongoing cost for running a product, business, or system. And the figure show these two, the sum of these costs. So basically, the profitability or of running the cost in running this a business based on this. And this is their solution based on radio frequency wireless forward transfer. This is a solution based on cables, and this solution based on batteries. As the number of years passed, the solution based on batteries decrease in the cost because of maintenance and replacement problems, waste, etc., etc. While for more than 2 years, we can see that this solution is most or the less costly, let's say. And these are very interesting trade-offs. So one key feature of a scalable low power radio frequency power transfer is that transmit channel state information free. I mean, we would need solutions that do not rely significantly on, I mean, that we avoid overhead. Because if we have an energy limited device and a base station, this has not sufficient energy resources to interchange information with the base station all the time or with our beacon. So we need to avoid unnecessary or unnecessary overheads signaling. And one of the key signals in modern radio communications is related to the acquisition of the channel state information. Because if we know the channel state information, then this base station or beacon can design efficient strategies to power the device or to transfer energy to the device, etc. Information to the device, etc. But again, this creates, if on this channel, you need to have active communication with the base station, and that drains energy, time. So the most important thing is not how much energy you can transfer, but how much energy can you use here after you do the transmission of energy and you spend energy in the communication. So for that, one of the things that has been promising are related to scenarios where the base station operates with limited information, like operating without any the channel or very limited information. The main solutions. Well, these are the main advantages of using, for instance, statistical knowledge of the channel or just the line of sight component of the channel. And basically because the statistical channel state information remains accurate over a large time scale in quasi-static or static setups. So you don't need to train the channel continuously, but from then to then. Can be predicted based on machine learning or other statistical methods. If you use the information regarding the line of sight channel, which is the geometric channel, which is these kind of channels are, I mean, when you have that are short in distance, these are more likely to be on the line of sight. If they are on the line of sight, that can be predicted mathematically based on the antenna rate and the distance and position modes. And instantaneous channel state information acquisition procedures can be run when system constraints are favorable, while relying on the channel statistics when such constraints become stricter, and these procedures are unaffordable. So that these are the advantages and the background why to use solutions based on free CSI or limited CSI information. One of the problems that we've been addressing is the obsession of the placement of multiple energy transmitters to charge their devices. So in this case, for instance, the